we present a novel method for simulating fluids with moderate to extreme surface tension effects. Our method is based on an updated Lagrangian formulation of the underlying continuum mechanics and is designed for hybrid particle grid fluid simulation techniques like the material point method. Physical quantities at a time t during a simulation can be expressed in terms of their deformation from a prior time, such as the initial configuration at time 0 or an intermediate configuration at time s. Using the updated Lagrangian view, the potential energy associated with surface tension at time t, which is proportional to the surface area of the fluid, can be expressed in terms of the deformation of the fluid boundary from a previous time s. Here, k sigma is the surface tension coefficient. To see how surface tension forces affect the fluid, we start from the variational form of the momentum balance equation in the updated Lagrangian view. In the material point method, the discretized momentum balance equation leads to a momentum update on grid nodes, which takes the form of the second equation here. In particular, we must evaluate the discrete total force acting on a grid node, where force terms may be written as derivatives of their corresponding discretized potential energies. The last equation shows the discrete energy terms for pressure and surface tension effects. We note that in this last equation, the first term sums over the standard MPM particles representing the fluid, while the surface tension term sums over a set of additional particles which are added to sample the approximate boundary of the fluid. We use a novel procedure for generating the boundary sample points where surface tension force is evaluated. We associate a spherical level set to each MPM fluid particle centered at the corresponding particle location. The union of these level sets yields an implicit representation of the fluid body, whose boundary can then be approximated as the zero isocontour of the level set, shown as the dotted green line. To reduce the boundary location error incurred from the radii of the particle level sets, we uniformly shift the level set, and hence the isocontour, by a multiple of the grid cell size, resulting in the solid red isocontour which more accurately fits the fluid particles. We subsequently sample this explicit boundary representation by selecting a number of points on each isocontour face in order to obtain a roughly spatially uniform distribution of boundary sample particles. These particles are flagged such that surface tension forces are evaluated exclusively on these particles. The sample particles are assigned zero mass, so they only contribute surface tension effects. We note that our boundary sampling technique only needs to be performed once per time step, so it is particularly efficient for the fully implicit formulation of our scheme where time steps are potentially quite large. We show a two-dimensional example of two colliding circular disks. Using a low surface tension coefficient, we observe dynamic topology changes as the disks separate and then re-merge. We render both the fluid particles as well as the boundary sampling particles for sake of exposition. With higher surface tension forces, the disks collide but do not separate, and tend to oscillate at higher speeds. In 3 dimensions, we first show a cube oscillating purely under surface tension forces. The geometry varies between a cubic and an octahedral configuration before settling into a spherical shape as numerical damping takes effect. We next show a falling ellipse of liquid metal at varying surface tension coefficients. With low or moderate surface tension coefficients, the topology of the fluid changes quickly, yet our formulation is able to robustly apply surface tension and preserve smooth fluid geometries as the simulations progress. We also demonstrate a one-way coupling example. As surface tension increases, the droplet's impact on the platforms tends to result in separation into multiple droplets, while with greater surface tension, the droplet becomes stiff. Finally, we present a fully two-way coupled example where a spherical fluid droplet falls on a cloth sheet. The cloth is weighed down by the fluid, and the liquid metal's motion is significantly altered by the presence and motion of the cloth.